Okay, so we're going to start by considering the question of statistical estimation on the exponential family. And the motivation for starting with the exponential family is that it has a lot of nice properties, and hopefully it helps to illustrate the basic ideas. So, as a reminder, we're looking at probability distributions of the form Px, and there's a parametric dependence on theta, which is the exponential of theta dot x minus phi of theta. So again, this phi is a normalizing factor, so that the probability distribution it's like has sort of integrates out to 1, right? So let's say you're given data. D, then the joint probability distribution can be written as follows. P d theta, right, is the exponential of n times theta dot x bar minus psi of theta. Oh, there's the n is multiplied into this normalization factor as well. And that's just because, it's like the joint probability distribution is just given by the product of these individual probability distributions for each of the xi's, right? And so I'm writing it's like this theta, it's like dot xi term as theta dot x bar times n, all right? And that's the only thing I'm doing here. So where x bar is the arithmetic mean of the observed examples. Okay, so x bar is just 1 over n times the sum from I equals to 1 to n of xi. Okay, so this is a sufficient statistic. Okay, so you can ask, what is the maximum likelihood estimator? So the maximum likelihood estimator for theta right is given by differentiating the joint probability distribution. And is given by eta is equal to the gradient of phi, theta equals to x bar. Okay. So, so using the eta coordinates, this is written as eta hat, right, is equal to, well, eta hat maximum likelihood estimator is equal to x bar. Okay. So what happens is that the observed data defines a point eta bar in M. Okay. With coordinates eta bar is equal to x bar. Okay. And this is the observed. It's like point. It's like from the data. So let's state the following theorem. Then the maximum likelihood estimator is unbiased and efficient. And if you recall, it's like this notion of efficiency has to do with the error covariance matrix and how it satisfies the the Kramer-Rao. It's like inequality. Well, it achieves, it's like the sort of the property, right? So the expectation of the maximum likelihood estimator, right, is the actual value, right? So that's what's meant by it being unbiased, right? In a statistical sense, right? And then the error covariance matrix is 1 over n times G inverse, where G is the the Riemannian metric, right? Well, right. Well, so technically G is the Fisher information metric. Yeah. Okay, so so we're not going to prove this. It's like, but this is relatively easy to show. Well, okay, let me just sort of give you a sketch of how one might do this. All right. So basically, you evoke the central limit theorem. And conclude that eta bar, right, is asymptotically sort of described by a Gaussian distribution with mean eta and covariance matrix. G inverse divided by n. Okay, and then since the maximum likelihood estimator attains the Kramer-Rao bound, it's the best estimator in the exponential family. All right, so one thing which is worth remarking is that here it's like we've expressed it's like this discussion in the context of the eta coordinates, which is the dual coordinate system. You can ask it's like what happens if you were to try to do this, it's like in the theta coordinates, which were the primal coordinates. And so it turns out that you get a slightly different answer. The estimator is not as nice. All right, so, and I'll say a little bit why that is, right? So the maximum likelihood estimator in the theta coordinate system is asymptotically unbiased. And asymptotically efficient. Right, which is in contrast, it's like to what happened in the eta coordinate system where it was unbiased and efficient, right? So this is a weaker condition, okay? But it is not unbiased. Nor does it attain the Kramer-Rao bound exactly. And the reason basically is that it's like the bias and the covariance matrix is coordinate independent, right? So this is because, well, more precisely, it's not that it's coordinate dependent, but it doesn't transform. It's like a tensor. Okay, so it's not really an intrinsic object, if you will, on the manifold. Not tensors. So, so their approximation properties depend on the choice of coordinates. Okay. All right. So this is again another reason why it's like whenever possible, we'd like to consider objects which are tensorial because they transform in a natural way under change of coordinates. Okay. All right. So anyhow, so that's just a quick introduction to what happens when you do statistical estimation. Now on one of these information manifolds, in particular one of the simplest ones which we've worked with, which is the exponential family. So we're going to continue along this vein a little bit. So let me just stop here for now.